variables. Today we're going to talk about interval of convergence. Continue talking about interval of convergence. We're just going to run a power series without actually writing down all the details of the power series. We want to know what's going to happen. Got to think about the stuff that gets left behind in the limit from the power series. So yesterday we had this example, and the x minus 4 to the n, that tells us where the center of the series is. So the center of the interval of convergence it's important to identify the center of the interval of convergence. The power series always converges there. If x equals 4, the power series converges because all the terms are 0. We always get convergence at the center of the interval. And that's the first thing we need to identify. Power series always converges at the center. For the finite radius of convergence, if we see other exponential stuff, that's going to be left over as a constant in the ratio test. So this 2 to the n in the denominator, that's going to leave a 1/2 in the limit from the ratio test, and then we're going to multiply both sides by 2. So a 2 in the denominator means our radius of convergence is going to be 2 without any factorials to give us zeros or infinity. So that 2 to the n in the denominator, that's going to tell us the radius of convergence will be 2 if it's finite. There's no factorials, so we're going to go with this radius of convergence of 2, a finite radius of convergence. If we don't have that 2 to the n, the default radius of convergence is based on the exponential stuff in the top, and the default radius of convergence is 1. Because we're not going to leave any constants behind. The square root of n plus 1, that's going to tell us about the endpoints. Polynomial and radical stuff tells us about the endpoints. So the radius of convergence is 2. That tells me above we're going to have 4 plus 2 is 6. And 4 minus 2 is 2. A little far. So we're getting all this stuff in between 2 and 6. Then we have to decide if the endpoints are included or not. And for that, we have to look at the polynomial and radical stuff, the stuff that the ratio test can't see. What usually happens is that one end is just the polynomial stuff, and the other end will be the alternating version of the polynomial stuff. One end is alternating, the other end is not. It matters because this is a square root. So at one end, we'll get 1 over the square root of n. And at the other end, we'll get the minus 1 to the n over the square root of n. So we want to be able to identify which one is the 1 to the n and which one is the alternating. In this case, the alternating is conditional convergence, which means that the alternating n is in that case, that's going to be the 2. That makes it negative 2. So the 2 is included, but the 6 is not. In this case, the alternating is what got us convergence on the part with 2. So the interval of convergence, 2 is the bottom end and included. And at the top we have 6 and it's not included. So our interval is half open or half closed. Since our interval is half open or half closed, we don't get to use absolute value inequalities. Absolute value inequalities would require both of these be the same. So here's what we write. Good question. So we want to identify all the things that we need to identify just by looking at the power series. There's nothing different in this series than there was in the previous one. We've got the power series part, the x plus 3 to the n. We've got an exponential factor of 5 to the n in the numerator this time, but that's not a thing. And we've got a polynomial factor, n squared this time. But that's how we categorize the 3 things that are going on here. The x plus 3 to the n is going to tell us that the center of the interval is at negative 3. There's a 5 to the n in the numerator, so we're going to have to divide by the 5 that's left over. And that makes the radius of convergence 1/5. So we're going to have negative 3 and 1/5 and negative 2 and 4/5. In this case, at one end, at the end point, one end will be a 1 over n squared, which is absolutely convergent. The other end will be a negative 1 to the n over n squared, which is also absolutely convergent. Alternating is the primary way we get conditional convergence, but we should always be looking for absolute convergence first. So the alternating doesn't matter because the absolute value is a 1 over n squared, and that's still convergent. Alternating will make it converge faster, but that doesn't matter. We get absolute convergence. So both endpoints are included in the interval of convergence. So here, we can say the interval of convergence is -3 1/5 less than or equal to x less than or equal to -2 4/5. Since both endpoints are included, we could list the interval of convergence as x plus 3. The absolute value of x plus 3 is less than or equal to 1/5. Previous example, the absolute value of inequality was not available for use because we only had a half open interval or a half closed interval. Questions? Remember what we're thinking about. We're thinking about running the ratio test without having to run the ratio test. Be so proficient at running a ratio test that you can see what the answer is going to be. 5 at the end is going to leave behind a 5. X plus 3 to the end will leave behind an absolute value of x plus 3. In the ratio test, the n squared in the denominator, we just have a limit as n goes to infinity of n squared over n plus 1 squared. And that limit's going to be 1, so that's not going to get us anything from the ratio test. That's the ratio test being blind to polynomial and radical factors. Think about what gets left behind in the ratio test. Think about what's going to be left behind in the ratio test. Exponential stuff leaves behind constants. Polynomial stuff doesn't matter in the ratio test. Factorials leave behind n. So it starts off the same, 5 at the end, x minus 3 at the end. We're already thinking middle is -3. Radius is going to be a 1/5, but then we look in the denominator and it's not polynomial. We look in the denominator and there's a big factorial bomb sitting right in the denominator. In the ratio test, factorials leave behind n's. This is going to leave an n in the denominator. So the limit from the ratio test is going to go to 0. Whatever we put in for x, the ratio test is going to go to 0. Factorials leave behind n's in the ratio test. All this exponential stuff on top, but then we look in the denominator to see that n factorial. and n factorial wins. This power series always converges. So we either say all real numbers or interval notation. For all real numbers. If you want to indicate all real numbers, you make the fancy double barred R. It's just a regular R with an extra vertical line. Makes it look fancy. We started doing this because we started getting tired of writing all real numbers all the time. So much writing, let's just make a fancy R. Then we high five each other. But when I went out and got coffee. I'm just kidding, I wasn't there when this decision was made. It becomes a problem because we call fractions rational numbers. And so it's like, well, let's name the rational numbers. We'll just use it. Damn it. So we use the next logical choice. Q is the rational number. So let's see the ratio test. Let's see this n get left behind in the ratio test. We'll take the limits as n goes to infinity of the absolute value of, we'll have a n plus 1, so 5 to the n plus 1 times x plus 3 to the n plus 1 over n plus 1 and then factorial. Now the exponential stuff, when it cancels out in the ratio test, leaves behind 1 power. 5 to the n plus 1 over 5 to the n will leave behind a 5. X plus 3 to the n plus 1 divided by x plus 3 to the n will leave behind an absolute value of x plus 3. Both of these factors no longer involve n, so I can take them out of the limit and then goes to infinity. 5, an absolute value of x plus 3 said, hey, all of our n's cancel it out. Can we get out of here? And the limit's like, oh yeah, get out of here. When we simplify n factorial over n plus 1 factorial, we write the bigger factorial until we get to the smaller factorial, and then the smaller factorial cancels out. That n factorial left an n behind in the limit from the ratio test. So now as n goes to infinity, whatever we have for x, this limit will go to 0. And 0 is always less than 1. Remember, we're thinking about large values of n. And we want to start seeing these factorials as being even bigger than exponentials. At this point in your mathematical career, exponentials are like the kings of speed. 5 to the n grows ridiculously fast. If we have an n to the 5th, compared to a 5 at the end. When n is a billion, then a polynomial is a billion to the 5th power. But when n is a billion, 5 at the end is a billion copies of 5. That's way bigger. I don't have just five factors. I've got a billion factors. When we look at a factorial, n factorial, when n is a billion, we have also got a billion factors, most of which are bigger than 5. Because the 5 is just a billion 5. It's 5, 5, 5, 5, 5, 5, 5, 5. Okay, last time I did that, it took me like years to finish. So just imagine a billion 5. But with a billion factorial, there's 5, 4, 3, 2, and 1 at the very end. But then there's also a 6, a 7, an 8, a 9, a 10, an 11, all the way up to a billion. Most of the factors are way bigger than 5. Factorial is going to win. Questions? In season 1, exponentials can be your villain. But in season 2, where you have to raise the stakes, you need to introduce the factorial. So that the audience is like, whoa, this is way worse than that exponential bad guy from the last one. You can introduce this with the Worf effect. Does anyone know what the Worf effect is? Everybody know who Worf is on Star Trek: The Next Generation? He was a Klingon, and he was big, tough, and strong. But the reason that he was there was to show how big, tough, and stronger some other alien race was. Because if you had an alien race that you wanted to be really frightening, all they had to do was throw Worf across the room. That was shorthand in Star Trek for these guys are dangerous. Because Worf is scary. He's supposed to be like, whoa, he's the strong one. He's fucking Klingon, for Christ's sakes. He's supposed to be able to just kick everything's ass. And then this alien comes in, and Picard's like, oh, whoa, kick its ass. Worf goes in and it's going bash, like right across the room. You know what would be really nice is if they had some scenes where they just showed Worf beating some stuff up. Because then it would be more clear that Worf is supposed to be badass. So instead of telling us that Worf is a badass, show us that Worf is a badass. Then it'll have more impact when some alien comes in and like throws him across the room. You know what I mean? A lot of times we come up with these ideas for characters like, oh yeah, these characters are badass. But then we have to be told that they are. Like in Star Wars, Captain Phasma is supposed to be scary, not impressed. Never did anything in front of the audience that would indicate, except for the fact that she gets to have chrome armor. Maybe she's just rich, and she's like in real life, she'd just be driving around in a chrome Lamborghini because someone said, drove their Lamborghini into a shop and said, I want this to be chrome. And instead of doing the rational humanitarian thing, saying no, they're like, ugh, that's gonna be horrible. I'll give you this much money right away. One chrome Lamborghini coming up. You know what I mean? I don't know. It's not a strong enough communication. How can I consider myself a Star Wars fan when I have such strong criticisms of most of the movies? I don't understand this at all. Like Walking Dead turned south, and I just abandoned it. It was fine. Game of Thrones kind of went off the rails. I just let it go. Why am I still a Star Wars fan? I have such strong criticism for most of the movies. For the longest time, my favorite Star Wars movie was that video game, Knights of the Old Republic. And I thought that would have made a better movie than the first 3 movies. Not filming that like with actors and stuff, just putting a camera behind some person playing Knights of the Old Republic, making 3 movies out of that, that would have been a better movie. Even with the bad graphics, because let's face it, we were pretty ambitious in 2000 with our computer graphics. look what we can do. And then like 5 years later, it's like, whoa, that looks terrible. You know what I mean? But then the Mandalorian came along. It's like, wow, cool. Then a Skywalker had to show up. Son of a bitch. Can we get rid of these? Questions? Not about Star Wars. About finding the interval of convergence. By running a ratio test, by not running a ratio. How's everybody okay? That's okay. No, it's remember, so let's take a look at just that piece of things. And let's look at a series, not a power series, of just 1 over n factorial. So the canceling thing is specific to the ratio test. Remember, in a ratio test, we're going to do the limit as n goes to infinity of an plus 1 over an. I actually don't want to do 1 over n plus n factorial. I want to isolate the factorial stuff. Let's just do n factorial, even though the limit doesn't go to, the limit's not going to exist. We want to see the factorial stuff. So change your 1 over n factorial to just n factorial. It's going to diverge. The terms don't go to 0. That's not what we're exploring right now. So an plus 1 is going to be n plus 1, then factorial. And an is just n factorial. Instead of using the recursive definition for n factorial, let's write down what n plus 1 factorial means. That's going to start off with n plus 1, then n minus 1, then n minus 2. It's going to be that product. So I'll have n plus 1 times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. That's what n plus 1 factorial will look like. N factorial has all of these factors except for the n plus 1. Everything that n factorial has, every factor in n factorial is also a factor of n plus 1 factorial. And so the n cancels the n minus 1, n minus 1, n minus 2, all the way down to 3, the 2, and the 1. And so the only thing that's left is that n plus 1. In this case, this limit goes to infinity, which we're thinking of as being greater than 1. But our goal here was not to determine if the series converges or diverges. Our goal was to think about how n plus 1 factorial and n factorial combined in a ratio test. If we think about it in terms of numbers, we're thinking about 4 factorial over 3 factorial. We use a smaller one. 4 factorial is 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. So we're just left with a 4. We have 8 factorial over 7 factorial. That's 8, 7, 6, 5, 4, 3, 2, 1. And 7, 6, 5, 4, 3, 2, 1. So that's how the factorials are going to interact in a ratio test. Not in a ratio test context, but if we think about a difference of 2, like if we have n plus 2 factorial divided by n factorial, I've got to write down 2 factors until I get to the n factorial. And so we're left with 2 factors, an n plus 2 and an n plus 1. This is why I say our strategy for simplifying the factorial stuff in the ratio test is to write the bigger factorial until you get to the smaller factorial. And then cancel out the smaller factorial. So if you have 10 factorial over 8 factorial, you'll have 10 times 9 left over. You have 10 times 9 times 8 factorial divided by 8 factorial, and everything 8 and less. Separating out 2 factors, the difference of 2 between your factorials so that 2 factors get left behind. That could happen if we had something like a 1 over 2n factorial. Because here, an is going to be just 1 over 2n factorial, but an plus 1, I'll have 2 times n plus 1 and then factorial. So we add 1 to the n, then we multiply 2, then we factorial. So notice that our an plus 1 is actually a 2n plus, the factorial of 2n plus 2. The factorial of the sum of twice a number and 2. So in this case, we write the bigger factorial until we get to the smaller one. So the 2n plus 2 factorial is the bigger one. So we start off 2n plus 2. The next factor is 2n plus 1. And then the next factor after that is 2n, then 2n minus 1, then 2n minus 2. That's where we're going to start canceling everything out. So 1 over 2n plus 2 times 2n plus 1. So 1 over 4n squared, that'll go to 0. Everybody okay? So factorials can only be counted with other factorials. So we have to look at how the factorials are going to interact with other factorials. But once we see some factorials running around in our power series, if we see a factorial in the denominator unchecked by a factorial in the numerator, then that's going to start looking like that power series converges for all real numbers. An infinite radius of convergence. Because the limit from the ratio test will be going to 0. If the factorial is in the numerator with no factorials in the denominator to keep it in check, then it looks like that limit is the limit from the ratio test is going to go to infinity, which will be greater than 1, unless we zero out all the terms, because a power series will always converge at the center. Is everybody okay? What do we think of power series? Look how long you have to wait between the time that you study polynomials and the time those polynomials can just keep on going. Like it's way back in algebra that you learn about polynomials. But the polynomials stop at some degree. Here we finally get to the point, what if the polynomial just keeps going forever? Okay, okay. Where you get to sequences, series, and power series, it really sits apart from the calc that we looked at before. Calculus before was like derivative calculus, integral calculus. Thinking about derivatives, going in the derivative direction with rates of change, going in the other direction with total change. But we had to find another place to put this kind of infinity. This is the same, we're studying this a different kind of infinity. The infinity that we studied in differential and integral calculus is things that are getting infinitely small. So we have an infinite number of things that keep getting thinner. Here we have an infinite number of things. They're all the same distance apart. Because, well, not the same distance apart, but we have a discrete infinity that we're looking at. Before we were trying to study the continuous. We had to understand infinity to study the continuous. Now we're just studying infinity in a discrete fashion. Except for the fact that we relied on something like the integral test, we could have led with this. I could have said, calculus is the study of infinity. Here are some things. Here are series. There's an infinite number of terms. What does that mean? Calculus is kind of the study of rates of change. That's its primary focus. But I think that definition came along because people are like, oh, look, derivatives, integrals, rates of change all over the place. But then sequences, series, and power series come up and say, what's up? And we're like, oh, wait, that's not really rates of change, is it? You know what I mean? There's never really one good frame. You just keep backing out and backing out. I've just taken one step further back. It's more than just rates of change. It's how we study infinity. This is the first time you're in a math class and you're talking about infinity as a rigorous concept, not just as some idea. You know what I mean? So yeah, primarily our study of calculus is about change. So your most common short description of calculus is that calculus is the math of how things are changed, the study of rates of change. But what are we really trying to study? What do we need to understand to study rates of change? We need to understand infinity. And so I prefer to think of calculus less as an engineering exercise studying rates of change, or physics exercise studying rates of change, and as a mathematical exercise studying infinity. This is because I'm 100% biased because I'm a math guy. My degrees are in math. And physics and engineering, I never really got along with physics and engineering, because in engineering, you're supposed to build stuff and it's supposed to work. And in physics, you're supposed to do experiments, and the experiments are supposed to work. And the same thing in chemistry. Like in chemistry, like you're supposed to put some stuff together, and the experiment is supposed to, what's the word? Work. And Michael, I know what's supposed to happen. Can't I just stipulate? Defense stipulates that I know that I'm going to have the same mass of salt at the end. They're like, oh, no, you actually have to do it. Michael, that's a physical skill, and we ain't got time for that. Because if you want me to pick up a physical skill, we're going to be here for a long time. Can't I just like explain, show you the calculations? And then they're like, oh, maybe engineering isn't for you. You know what I mean? But it was the 80s. And they're like, oh, you're proficient in math and science? I'm like, oh, yeah, kind of. But all I've ever done is math in high school and physics in high school. They're like, oh, that's fine. You'll love engineering. And I was like, oh, okay, I'll love engineering. What do engineers do? They make lots of money. I'm like, oh, okay. I mean, that's how you sell something to a high school kid. You will make money. Oh, yeah. Then I started looking into it. What do engineers do? How can you be like 2 years into an engineering degree and be like, oh, what is it that engineers do? Then you find out, I'm like, oh, work 100 and something hours a week. That's when I hit the reject button. I'm not here to do work. I'm here to sit around and think. Then I got the ultimate job. I just sit around and think and at other people. You know what I mean? All right, that's going to do it for today. That's going to do it for this week. I'll see y'all on Monday. Weekend, and thanks for playing.